Hello, viewers. Hello. Hola. I will begin in just a moment. I'm replying to my brother's text message. Good morning. What's up? Have you guys ever seen the WhatsApp commercials? If you haven't, after this lesson is over, you got to look up the WhatsApp commercials. They were a classic. I think they were Super Bowl commercials. All right, we're at 20 viewers. So I'm going to start. So we're done with forces. I think it was before you were born, but it's still it's a classic. There was also a classic commercial. So I actually know the Spanish verb querer because of a Taco Bell commercial that had a Chihuahua in it, and the Chihuahua would go, "Yo quiero Taco Bell." So, anyways, okay. So today we're going to talk about. We're done with forces, and we're going to talk about energy. Okay? And in particular, the topic of today's lesson is potential energy. So, potential energy. What's up, Bugs? What's up? Oh, okay. Potential energy is energy due to your position. Okay? So the variable for potential energy is U. Okay? And it's a function of position, so we say U of X. Okay? Um, so the first thing I want to talk about is how is potential energy related to force? How is potential energy related to force? Um, well, and this is a definition, okay? So don't get all freaked out by this, okay? It's a definition. There's nothing mystical about it. It's just a definition. Um, okay, the force is equal to minus the derivative of the potential. Okay? So if a u of x satisfies this equation, then it is called a potential energy function. Okay? So there's nothing mystical about that. It's just a definition. So if you happen to find a function, u of x, such that when you do negative the derivative of it, okay, it equals the force on an object, then good job. You found the potential energy function. Okay? All right. So this is our sort of our guiding equation today. All right. So let's just do a really brief example. So an example, what if u of x equals 3x squared minus 7x? What is the force on a particle at x equals 2 meters? So if the particle is located at x equals 2, what is the force on it? Well, what we would do is we would use this equation. All right. So F equals minus the derivative of the potential. So we have to do that derivative thing. So taking the derivative, if you recall, means bringing the power of x down and then reducing the power by 1. Okay, so we have 2 times 3 times x to the 1. Bringing the power down, in this case the power is 1. So minus 7 times 1 times, and then we reduce the power, x to the 0. X to anything to the 0 power is 1. So we get that this is minus 6x plus 7. Okay? So now we want to know what is the force at x equals 2. F of 2. That's not times 2, it's of 2. So we would plug in minus 6 times minus 6 times 2 plus 7. Okay, so that would give us a force of minus 5 newtons, or 5 newtons in the leftward direction. All right, so that's very simple. And this works for at least 2 of the forces that we already know about. So, for example, actually, I'll come back to this later. Okay. Next thing I want to do is I want to definition of kinetic energy. So we discussed kinetic energy last year, and it's denoted by K, and its value is 1/2 mv squared. All right. So now I'm going to show you guys one of my favorite proofs. I'm going to do a proof for you guys. All right. Let me define total energy first. Definition of the total energy total energy is denoted by E, and it is equal to the kinetic energy plus the potential energy. Okay? So what I would like to do to you is I would like to prove a nice little theorem. So the theorem is this. Energy is conserved. I'm going to prove it to you. And just in case you forgot, to say that something is conserved means that its value does not change as time goes on. Okay? So in particular, if something is conserved, that means that its time derivative is 0. The derivative of the energy with respect to time is 0. Okay? So that's another way of saying that something is conserved. So now I'm going to prove it. This proof is going to involve some calculus, so if you're new to calculus, don't worry about it. I'm not going to give you a final exam where I say, prove that energy is conserved. This is just showing you that we can mathematically prove that it's conserved. All right? So, so if we look at the energy is K plus U, kinetic energy plus potential energy. So that means that the derivative of the energy with respect to time is the derivative of the kinetic energy with respect to time plus the derivative of the potential energy with respect to time. Okay? So let's go ahead and go through what each of these terms is. Okay? What is the derivative of the potential energy with respect to time? Well, that would be the derivative of u of x, right? So notice how x, I'm taking the derivative with respect to time, but the potential energy is a function of position. So I have to do the chain rule, okay? So this is going to be du dx times dx dt. So that is the chain rule, okay? Now, du dx, according to the definition of potential energy, du dx is negative the force. Okay? So we have minus the force. And dx dt is the velocity. So the derivative of the potential energy with respect to time is negative force times velocity. Okay? So I can write, for this term, I can write negative FV. Okay? Cool, so we did that one. Now let's do the derivative of the kinetic energy with respect to time. That would be the derivative of 1/2 mv squared. Now, as you can see, the kinetic energy is a function of velocity. So again, we have to do the chain rule, okay? So we're going to do the derivative of the kinetic energy with respect to velocity, times the derivative of the velocity with respect to time, okay? The derivative of the kinetic energy with respect to velocity, well, that's the derivative of v squared. So we bring the 2 down, that cancels out the 1/2, and we get just mv is the derivative of the kinetic energy with respect to time, which happens to be momentum. I gotta look at the camera, I'm looking at myself, but it happens to be momentum is the derivative of the kinetic energy with respect to velocity. I wonder if some of you have noticed that before. That's not an accident. Times the derivative of velocity with respect to time is acceleration. So, okay, so the derivative of kinetic energy with respect to time is mva. Now let's go ahead and factor out velocity, because velocity is here and it's here. It's in both terms. So factoring out the velocity, I get ma minus f. But ma minus f is 0 according to Newton's second law. F equals ma. So ma minus f is 0. So we just get 0. The derivative of the energy with respect to time is 0. So energy is conserved. QED. Proof is done. All right. So this is really probably one of my favorite proofs. I enjoy this one a lot. When I saw it for the first time, I was like, and I hope it does that to you a little bit as well. Okay. And, oh, I just thought of a really good problem. Okay. So the thing that I want to point out is that the reason that energy is conserved is because of Newton's second law. So saying that energy is conserved is not a, it's not some mystical statement, okay? Energy conservation is only true because of Newton's second law right here. So Newton's second law is more fundamental than energy conservation, at least at this current level of understanding of physics that we have, okay? So, and then energy is really just a function that we built, okay? We discovered a function that is k plus u that happens to have 0 derivative with respect to time, okay? So, anyways, I find that very pleasant. So we know that energy is conserved. All right, so let's go to our next topic for today, which is u of x graphs. And this is kind of a fun subject, I think. All right. So we're going to draw a graph of the potential energy as a function of x. So maybe it looks like this. That's an example of what it might look like. Okay. Now let's try to interpret this. All right. So this is potential energy versus position. Now the force is minus the derivative of the potential. Okay? So it's equal to minus the slope. So if you're not in calculus, it's just minus the slope. So we can see that here the slope is positive. So minus the slope is negative. So the force at this particular location is negative. Okay? The slope at this particular location, the slope is negative. So negative is positive. So the slope is positive. Okay? Here, the slope is positive. So negative, the slope is negative. Here, the slope is negative. So the force is going to be positive. Okay? Now, I'm going to wait a moment for someone to type it into the chat. What about right here, and right here? What is the value of the force at those 3 locations? It's 0. Excellent. So the reason that it's 0 is because the slope is 0 at those points. It's flat at those points, okay? So these are 0 force locations. So basically, the conclusion is that the maxima and the minima of U of x represent points of equilibrium. Okay? They represent points of equilibrium. So when I say equilibrium, equilibrium means if you were to put the object there, if I were to put an object right here, it's not going to move because it has no force on it. Okay? But really there are two types of equilibria. There are what are called stable equilibria, and there are unstable equilibria. Okay? And this is an example of an unstable equilibrium. Now, why is that? Well, if we think about it, can I just give you a really useful way to think about this? Is we can think about the direction of the force as basically like a ball on a hill, okay? Because if you put a ball right here, which way would the ball roll? It would roll to the left, okay? The force is to the left. What if you put a ball right here? It would roll to the right. What if you put a ball at the bottom of the valley? It would just sit there. What if you balanced a ball perfectly right here? It would just sit there. So the way you want to think about it is you want to think about it as a ball rolling on a hill that is described by the U of x function. Okay, that's it. Now the particle isn't actually going up and down. This is just a mental representation to help you see what's going on quickly. Okay, so yeah. Now this peak is an unstable equilibrium. So why? What would happen to a ball if it's on top of a hill and you nudged it just a little bit? Well, it would then roll away from the top of the hill. If you nudged it to the left, boop, it would roll away from the top of the hill and it would never come back. Okay? So an unstable equilibrium is one where a tiny poke will make the object go away and never come back. All right? However, if we put the ball right here and we poked it, boop, it's going to do one of these things. It's going to go, so it stays close. It's going to oscillate. It's going to execute simple harmonic motion about the equilibrium. Okay? So basically you have stable and unstable equilibria. The minima are the stable equilibria, and the maxima are the unstable equilibria. Okay? So that's how that works. Now let's see, how does energy come into play? How does conservation of energy come into play? Well, we know that energy is kinetic plus potential, and it is equal to a constant. Okay? So in particular, if the potential energy goes up, then the kinetic energy goes down. If the potential energy goes up, then the kinetic energy goes down. But here's the thing. Okay? Here's the thing. The kinetic energy The definition of kinetic energy is 1/2 mv squared, and mass is always positive. Velocity squared is always positive because it's the square of something. So the kinetic energy is always greater than or equal to 0. Okay? So the potential energy can only go up so high, because if the kinetic energy drops, eventually the kinetic energy will become 0. And it can't go below that value. Okay? So let's suppose that a particle has this much energy. This is the amount of energy that the particle has. Okay? Then that means that the particle is stuck between here and here. All right? Because what would happen if the particle went to this location? Now the potential energy is greater than the energy. You see what I'm saying? So for example, if you have the potential energy greater than the energy, then you get a situation where maybe the energy is 10, but the potential energy is 15. So that would mean that the kinetic energy is -5, which is not possible. Okay? So these locations where the potential energy equals the kinetic energy, these are called turning points. Okay? So this is a turning point. Because once a particle gets to that spot, it can't go any further to the right. So the particle would kind of, if you have a ball with this much energy, it would kind of go like that. Okay, so you're stuck between these two extremes. The difference between the energy line and the potential energy line is the kinetic energy. So whatever that difference is, that's the kinetic energy. How can I prove that? It's very simple. I just take this and I notice that kinetic energy is energy minus potential. So if I subtract these two, then I get the amount of kinetic energy. Okay? So this is how we can interpret potential energy graphs. Now here's something interesting. Well, what if, I'm going to redraw my graph here. So I have a potential energy graph. What if my potential energy graph looks like this again? What if my total amount of energy is this? Type in what you think in the live chat. Okay, I'm going to sip some coffee and close the window because I'm a little bit cold. Gonna wait a little bit longer to see if anyone has any thoughts. Okay, looks like no one knows. So, in this case, you basically have two regions. So the particle could go between here and here, or it could go between here and here, but it can't get between those two spots. So there's basically, the particle is stuck in one region or another region, but it can never get between them because it doesn't have enough energy to get over the top of this little bump to go from one side to the other side. All right? So that's kind of cool. Believe it or not, this actually... So one thing I wanted to say is that This is only true in classical mechanics, okay? In quantum mechanics, this is not a class on quantum mechanics, but I can't help myself because it's exciting. In quantum mechanics, it is possible for a particle to momentarily enter a region that is not allowed. So, for example, this space between the two regions where it has enough energy to go, it is possible to briefly enter that region and tunnel. This is the term, tunnel to the other side. Okay? So I'm going to tell you something that I find kind of trippy. So maybe there's a potential energy graph for the universe. Okay? All right? Maybe there's a potential energy graph for the entire universe. So the universe is in a certain configuration, and the universe is in an equilibrium configuration. So maybe the universe is right here. Okay. Yeah, good question. If it's able to go into, so this region right here is called the forbidden region. Okay. And yeah, you can find it in the forbidden region. It's just not likely to find it in the forbidden region. But the point is that you're able to have these in classical mechanics. You would never find it in the forbidden region, but in quantum mechanics, you can. And so, because it can go into the forbidden region, it can actually get to the other side. So, anyways, what if this is our universe? Okay, and this is the amount of energy of the universe. Then, according to quantum mechanics, if this were the shape of our potential energy graph, it would be possible for the universe to tunnel into a different configuration corresponding to this equilibrium. Okay? Which would mean that, so what would happen if our universe tunneled to another equilibrium? It would mean that the configuration of the universe would just all of a sudden just go and change, and we would all be destroyed. Basically, reality as we know it would just completely change all of a sudden, and you wouldn't experience anything because you would just cease to exist. But yeah, I think that's kind of an interesting thought, is that the universe could tunnel to another equilibrium if this is the shape of its potential energy graph. One of the things that quantum mechanics is able to tell you is what is the tunneling probability. So what is the likelihood that this transition could happen? And also it would tell you what is the time it would take for that tunneling event to occur. And one of the things we can say is that the time for the tunneling to occur is at least 13 billion years, because that's the age of the universe as we know it. So, maybe the Big Bang was the universe tunneling. I don't know. Maybe the Big Bang that started the universe was really just tunneling from a previous equilibrium position. I wanted to give you another example of U of X graphs. So a U of X graph that you see in nuclear physics is this. one that looks like this. So x in this case is distance from the nucleus. Okay? And then maybe this is the energy of an alpha particle. Okay? This is the energy of an alpha particle. An alpha particle is just it's a helium nucleus. Okay? Now, if the energy of the alpha particle is this amount, okay, then what would happen? The alpha particle would approach, it would hit the turning point, and it would come back. Okay? So what you would have here, and remember, the nucleus is positively charged, and an alpha particle is a helium nucleus, which is also positively charged. So they electrically repel each other. Okay? So they approach, and then they bounce off each other. Okay? But what if we gave the alpha particle more energy, and it actually has enough energy to get over the hump? Okay? So this is a different amount of energy. This is E1. This is more energy. If we give the alpha particle more energy, it is able to overcome the electrical repulsion, and then it actually gets pulled into the nucleus. And the thing that causes it to get pulled into the nucleus is called the strong nuclear force. Okay? And in that case, it can actually get pulled into the nucleus. And if it's in this region right here, there's a probability that the alpha particle won't come back out. It'll actually fuse to the nucleus. So this is how fusion occurs. Okay? Notice how you need to give the alpha particle enough energy to overcome electrical repulsion and get in close so that the strong nuclear force can pull it in. Okay? So generally speaking, how do you give the alpha particle, enough energy to get pulled in? Well, you make it hot. That's why fusion occurs in places like the center of the sun. The center of the sun is hot enough where the alpha particles have enough energy to actually get in and fuse. Okay. Yeah, so I think that's interesting. That's why all fusion reactors have to be extremely hot, because you have to give the particles enough energy to fuse. All right. So the idea of cold fusion does not really seem, if you've ever heard of cold fusion, it's kind of like a pie in the sky dream. And for cold fusion, it doesn't really seem that it would be possible. It doesn't really seem to have a theoretical foundation at this point, because you need to get over that hump. Now, of course, there is a tiny, tiny probability that the alpha particle could tunnel through this and fuse, but that's a low probability. So, yeah. All right. So that's my lesson for today, and I will see you in the Zoom room.